Welcome to this problem walkthrough. In this session, we'll tackle LeetCode number 1133, largest unique number. Together, we'll explore the problem, discuss multiple solution strategies, and break down the most optimal approach step by step. Let's dive in. The problem we're solving here is to find the largest unique number in a given integer array nums. A number is considered unique if it appears exactly once in the array. If no such unique number exists, we should return -1. Now, looking at the input format, the array nums can have a length between 1 and 1000, and each number in the array can range from -10,000 to 10,000. The output will simply be an integer, either the largest unique number or -1 if no unique value is found. For example, in the input array 5, 7, 3, 9, 4, 9, 8, 3, 1, the output is 8. This is because 8 is the largest number that appears exactly once in the array. To understand the example better, let's break it down. In the array 5, 7, 3, 9, 4, 9, 8, 3, 1, the numbers that appear exactly once are 5, 7, 4, 8, 1. Among these, the largest number is 8, so the output is 8. Now consider a different input, 9, 9, 8, 8. Here, there are no numbers that appear exactly once. Both 9 and 8 appear twice, so the output is -1. This shows how we handle cases where no unique numbers exist. Lastly, in the array 3, 5, 7, 3, 5, 7, 10, the only number that appears exactly once is 10. Since it's the only unique number, the output for this array is 10. Now let's look at the constraints and some edge cases. The constraints remind us that the array length is between 1 and 1000, and the values range from -10,000 to 10,000. Regarding edge cases, consider an array where no unique numbers exist, like 2, 2, 3, 3. Here, the output should be -1 because all numbers appear more than once. On the other hand, if every number is unique, such as 1, 2, 3, 4, 5, the output should be the largest value, which is 5. For single-element arrays, like 7, the single number is unique, so the output will simply be that number, 7. The problem also handles arrays with negative numbers. For instance, in -10, -20, -30, -10, the unique numbers are -20 and -30, and the largest unique number is -20. Similarly, in arrays with a mix of positive and negative numbers like -1, 2, -1, 3, the unique numbers are 2 and 3, so the output is 3, as it's the largest. These examples highlight that the solution should work seamlessly across all cases, whether the values are positive, negative, or mixed. This ensures the logic is robust and handles edge cases effectively. To solve the problem of finding the largest unique number in an array, we started by considering a brute force approach. The intuition behind this method is straightforward. For each number in the array, we determine its frequency by iterating through the entire array. If the number appears only once, we check whether it is the largest unique number encountered so far. Finally, we return the largest unique number, or -1 if no such number exists. While this approach is simple and easy to implement, it comes with a significant drawback: it relies on nested loops to calculate frequencies, resulting in a time complexity of n squared. This makes it inefficient for large arrays. On the other hand, its space complexity is 1, since no additional data structures are required. Although this method is conceptually clear, its trade-offs make it less practical for large-scale inputs due to its poor performance in terms of execution time. To address the inefficiencies of the brute force method, we considered an optimized approach using a hash map. By leveraging a hash map, we can store the frequency of each number in the array in a single traversal. This eliminates the need for nested loops, significantly reducing the time complexity. Here's how it works. First, we iterate through the array to populate the frequency map, where the keys are the numbers and the values are their frequencies. Next, we examine the frequency map to identify numbers that appear exactly once, keeping track of the largest such number. Finally, we return the largest unique number, or -1 if no unique numbers are found. This approach achieves a linear time complexity of n, as the array is traversed twice, once to build the frequency map and once to find the result. However, it does require additional space to store the hash map, leading to a space complexity of n. This trade-off makes the method particularly useful for large, unsorted arrays where time efficiency is more critical than conserving space. Another approach we explored involves sorting the array first. Once the array is sorted in descending order, identifying unique numbers becomes easier because we can compare each element with its neighbors. The steps are as follows. First, sort the array, then traverse it to check whether each number is unique, and return the first unique number found. If no unique numbers exist, return -1. The time complexity for this approach is n log n, primarily due to the sorting step. Its space complexity depends on how the sorting is implemented. If done in place, it's 1, otherwise, it's n, if a new array is created. While sorting simplifies the process of detecting unique numbers, it is slower than the hash map approach for unsorted arrays. However, if the array is already sorted or nearly sorted, this method may be advantageous. After evaluating these approaches, we chose the optimized method using a hash map as our final solution, as it provides the best balance between time and space efficiency. Sorting remains a viable alternative in specific scenarios, while the brute force approach is generally impractical for large inputs. The key insight that guided our solution was recognizing the importance of frequency counts for identifying unique numbers. By using a hash map, we could compute these counts efficiently in a single pass through the array, avoiding the need for nested loops or sorting. This realization was a pivotal moment, as it allowed us to design a solution with linear time complexity, making it both fast and scalable. The hash map approach not only simplifies the process but also ensures that the solution is robust and adaptable to inputs of varying sizes. This aha moment helped us eliminate less efficient strategies and focus on delivering an optimal solution for the problem. In this problem, we need to identify the largest unique number in a given array. A unique number is one that appears exactly once in the array, and if no such number exists, we return -1. Let's break down the approach to solve this. First, we need to understand the input and output. The input is an array of integers, and the output is the largest integer that appears only once in that array. If there are no unique numbers, we return -1. To solve this, we use a frequency map, or hash map, to count how many times each number appears in the array. Once we have this information, we can filter out the numbers that appear only once and then find the largest among them. The algorithm involves a few clear steps. First, we initialize a hash map to store the frequency of each number. The keys in this hash map will be the numbers themselves, and the values will represent how often each number occurs. Hash maps are particularly useful here because they allow for quick insertions and lookups with an average time complexity of 1. This efficiency is crucial for processing the counts of all numbers in the array in a timely manner. Next, we populate the hash map by traversing the input array. For each number in the array, we check if it's already present in the hash map. If it isn't, we add it with an initial count of 1. If it is, we simply increment the count associated with that number. This ensures that by the end of the traversal, the hash map accurately reflects the frequency of each number. This step is efficient, with a time complexity of n, where n is the length of the array. Once the hash map is built, we proceed to filter out the unique numbers. We initialize an empty list to store these numbers. Then, for each key-value pair in the hash map, we check if the value equals 1, indicating that the number is unique. If it is, we append the number to our list of unique numbers. This step narrows the problem down to only the numbers that appear exactly once, which simplifies the task of finding the largest unique number. If the list of unique numbers ends up being empty, we return -1 since it means there are no unique numbers in the array. Otherwise, we perform a simple linear scan of the list to find the maximum value, which is then returned as the result. The time complexity of this step is m, where m is the number of unique numbers, and since m is always less than or equal to n, the overall approach remains efficient. What makes this approach effective is its use of a hash map to count occurrences in n time, which is the most efficient way to tackle this aspect of the problem. Filtering unique numbers and finding their maximum is also efficient because it requires only a single pass through the hash map and the unique numbers list. This ensures that we handle the problem optimally. Some edge cases to consider include an empty array, where we immediately return -1, and arrays with no unique numbers or all elements being duplicates, which are naturally handled by our algorithm. For example, if no numbers have a frequency of 1, the unique numbers list will remain empty, and will return -1 as expected. The main data structure used here is the hash map, which is ideal for storing the frequency of elements due to its O(1) average time complexity for insertions and lookups. We also use a simple list to store unique numbers, which keeps the implementation straightforward. While alternatives exist, like keeping track of the largest unique number during hash map traversal, using a list makes the logic easier to follow and debug. To better understand the algorithm, let's walk through a couple of examples. First, consider the input array 4, 9, 2, 9, 4, 5. After constructing the hash map, we get 4, 2, 9, 2, 2, 1, 5, 1. Next, we filter out the unique numbers, which are the keys with a frequency of 1. This gives us the list 2, 5. Finally, we find the maximum in this list, which is 5, so the output is 5. Now take the input 7, 7, 7. The hash map here is 7, 3, meaning no numbers have a frequency of 1. The unique numbers list is empty, so we return -1. These examples illustrate how the algorithm handles both typical cases and edge cases. In the first example, it successfully identifies and returns the largest unique number, and in the second, it correctly identifies that no unique numbers exist and returns -1. Let's analyze the complexity of this algorithm. The time complexity is O(n) for constructing the hash map, followed by O(m) for filtering the unique numbers, where m is the number of unique numbers and m is always less than or equal to n. The total time complexity is therefore O(n), making the algorithm highly efficient. The space complexity is also O(n), primarily due to the hash map, with an additional O(m) for the unique numbers list. In total, the space complexity remains O(n). This efficiency ensures that the algorithm can handle large input sizes effectively. For edge cases, the algorithm handles scenarios like an empty array or all elements being duplicates by returning -1 when no unique numbers are found. If there's only one unique number, it simply returns that number. Optimizations are also possible, such as avoiding the use of a list to store unique numbers and instead tracking the largest unique number during the hash map traversal. This saves additional space. For sorted arrays, a two-pointer approach could be used, but it requires pre-processing and is less general. Overall, the presented algorithm strikes a balance between simplicity and efficiency, making it well suited for the problem at hand. This solution aims to find the largest unique number in the given array. First, we use a dictionary, frequency, to count how many times each number appears in the array. This is achieved by iterating over the array. If a number exists in the dictionary already, its count is increment, otherwise, it's added with an initial count of 1. After constructing the frequency dictionary, we extract all numbers that appear exactly once, unique numbers, using a list comprehension. Each key value pair from the dictionary is checked, and only numbers with a count of 1 are included in the unique _numbers list. Next, we handle the edge case where no unique numbers exist by returning -1 if the unique _numbers list is empty. Finally, if unique numbers exist, we return the maximum value from the unique _numbers list, which corresponds to the largest unique number in the array. This approach is efficient, as it processes the array in O(n) time to build the frequency dictionary and uses another O(n) pass to filter the unique numbers. The space complexity is O(n) due to the dictionary storage. The implementation is concise and handles edge cases such as an empty array or no unique numbers gracefully. This is the Java implementation of the largest unique number problem. The code mirrors the logic of the provided Python solution but uses Java-specific constructs like hashmap for frequency counting. Key differences include type declarations for variables and the use of Java's map entry for iterating over the hash map. The method follows the same approach, counting frequencies, identifying unique numbers, and returning the largest one, or -1 if no unique numbers exist. To solve this problem, we start by counting the frequency of each number in the given array. The input for this example is 5, 7, 3, 9, 4, 9, 8, 3, 1. We initialize an empty dictionary and iterate through the array to build it step by step. First, we encounter 5, so we add it to the dictionary with a frequency of 1. Next, we process 7, adding it with a frequency of 1 as well. Then comes 3, which is also added with a frequency of 1. When we reach 9, we add it to the dictionary, and the same happens with 4. Now, when we see 9 again, we increment its frequency to 2. Continuing, we add 8 with a frequency of 1, and then increment the frequency of 3 to 2 when we encounter it again. Finally, we add 1 with a frequency of 1. This gives us the complete frequency dictionary: 5, 1, 7, 1, 3, 2, 9, 2, 4, 1, 8, 1, 1, 1. Once we have the frequency dictionary, we extract the unique numbers by selecting those with a frequency of 1. From this dictionary, the unique numbers are 5, 7, 4, 8, and 1. Now that we have the unique numbers, the next step is to find the largest among them. The unique numbers, as determined earlier, are 5, 7, 4, 8, 1. To find the largest, we simply take the maximum value from this list, which is 8. Thus, the largest unique number for this example is 8. The final output for this input is 8. Moving on to the next example, the input array is 9, 9, 8, 8, 7, 7, 6, 6. Again, we begin by counting the frequency of each number. Starting with an empty dictionary, we process the first 9 and add it with a frequency of 1. When we encounter 9 again, we increment its frequency to 2. Next, we process 8 and add it with a frequency of 1, then increment its frequency to 2 after seeing it again. We repeat this pattern for 7 and 6, adding each with a frequency of 1 initially and then incrementing to 2 when they appear again. The final frequency dictionary for this input is 9, 2, 8, 2, 7, 2, 6, 2. From the frequency dictionary, we identify the unique numbers by selecting those with a frequency of 1. However, in this case, all numbers have a frequency of 2, so there are no unique numbers. This means the list of unique numbers is empty. Since there are no unique numbers, we cannot find a largest unique number. As a result, the output for this input is -1. Now let's analyze the third example, with the input array 10, 10, 20, 30, 30, 40. As always, we start by counting the frequency of each number. We initialize an empty dictionary and begin processing the array. First, we encounter 10 and add it with a frequency of 1. When we see 10 again, we increment its frequency to 2. Next, we process 20 and add it with a frequency of 1. For 30, we add it initially with a frequency of 1 and then increment it to 2 when we see it again. Finally, we process 40 and add it with a frequency of 1. The resulting frequency dictionary is 10, 2, 20, 1, 30, 2, 40, 1. Once the frequency dictionary is built, we extract the unique numbers by selecting those with a frequency of 1. From the dictionary, the unique numbers are 20 and 40. To find the largest unique number, we calculate the maximum of this list, which is 40. Therefore, the largest unique number for this example is 40. The final output for this input is 40. This completes our solution walkthrough for the largest unique number problem. Here, we analyze the time complexity of the solution by breaking it into 3 main steps. First, counting frequencies involves iterating through the input array ARR using a single for loop. Each element is processed once, and updating the frequency dictionary takes constant time on average, resulting in a total time complexity of O(n), where n is the length of the array. Next, we identify the unique numbers by iterating over the dictionary frequency.items. Since the dictionary contains at most n entries, this operation also takes O(n) time in the worst case. Finally, the max function is applied to the list of unique numbers. If all elements of ARR are unique, the list contains n elements, making this step O(n) as well. Each of these steps contributes O(n), setting the stage for combining the total time complexity in the next part. Adding the time complexities of the 3 steps gives us O(n) plus O(n) plus O(n), which simplifies to O(n). Now, let's look at the space complexity. The dictionary frequency is the first contributor, storing each unique element of the array as a key and its frequency as the value. In the worst case, where all elements of ORR are unique, the dictionary has n entries and requires O(n) space. The list unique _ numbers is another component, containing numbers with a frequency of 1. Again, if all elements are unique, this list also holds n entries, contributing another O(n) to the space complexity. These components are the foundation for determining the total space usage. In addition to the dictionary and the list, the solution uses a few temporary variables such as number, count, and the result returned by the max function. These variables require constant space, or O(1). When we combine all components, the total space complexity is dominated by the dictionary and the list, which results in O(n) plus O(n) plus O(1), simplifying to O(n). Comparing this with a naive approach, a solution using nested loops to count frequencies for each element would have a time complexity of O(n squared), since each element's frequency would require a full iteration through the array. However, the naive approach has a space complexity of O(1), because it doesn't use additional data structures. The optimized solution significantly improves time complexity to O(n), using a dictionary, trading off increased space usage of O(n). This trade-off is worthwhile for achieving linear time. Now, let's consider the best, average, and worst cases for this solution. In the best case, all elements in ARR are duplicates, meaning the unique numbers list remains empty and the max function is never called. However, the time complexity is still O(n), due to the frequency counting step. In the average case, where there's a mix of unique and duplicate elements, the time complexity remains O(n), because each element is still processed once. In the worst case, all elements are unique, which means the dictionary and unique numbers list both contain n entries, and the max function iterates over all n elements. Even in this scenario, the time complexity stays O(n). Mathematically, summing the individual time complexities O(n) for frequency counting, O(n) for list comprehension, and O(n) for finding the maximum confirms that the overall time complexity is O(n). Similarly, the space complexity is O(n), dominated by the dictionary and the list. This efficiency makes the solution robust across all cases. When working on this problem, there are several common mistakes to be aware of. First, not accounting for negative numbers can lead to incorrect results. Some might assume that all numbers in the array are non-negative, but the largest unique number could actually be negative if all other numbers are repeated. To avoid this, always ensure your solution considers the full range of possible values, including negatives and zeros. Another frequent error is mismanaging frequency counts. For example, using flawed logic to update or check frequencies can result in either misidentifying unique numbers or missing them entirely. This is why you should always use a reliable data structure, like a dictionary in Python or a hash map in Java, to accurately track the counts of each number. Finally, relying on inefficient sorting approaches can unnecessarily increase the time complexity. Sorting the array may seem straightforward, but it adds log n complexity, which may not be optimal. Instead, consider approaches like using a hash map to solve the problem in linear time. Another area to watch out for is properly handling edge cases. For instance, if the array is empty or contains only a single element, failing to check for these scenarios could lead to runtime errors or incorrect outputs. To address this, ensure you validate the input size and explicitly handle these cases. Additionally, it's important to define the correct return value when no unique numbers exist. If you forget to account for this case, you might return a value like 0 when the problem specifies -1 as the appropriate output. This can lead to failing test cases or introducing ambiguity in your solution. Always refer to the problem description to ensure that your return values meet the requirements. This problem also offers valuable insights for interviews. One key takeaway is recognizing the pattern of using a frequency map to identify unique elements in an array. This technique is a common theme in many array and hash table problems, so it's worth becoming familiar with. Interviewers often test your ability to handle edge cases, such as empty arrays with all duplicates, or those with just one element. Clearly explaining how you handle these scenarios demonstrates thoroughness. It's also a good idea to prioritize optimal solutions, like using hash maps, early in your discussion. While brute force approaches are simpler to derive, they may not be efficient enough. Discussing spacetime trade-offs is another way to show your understanding. For example, while a hash map offers O(n) time complexity, it also requires O(n) space. If space constraints are a concern, you might propose alternatives like in-place sorting. Finally, be prepared for follow-up questions. These might include variations such as finding the kth largest unique number or solving the problem with reduced space usage. This problem is related to several others that you might encounter. For instance, LeetCode 136, single number, requires finding the single element that appears only once in an array where all other elements appear twice. Another example is LeetCode 260, single number 3, where you need to find two unique elements under similar conditions. Problems like LeetCode 451, sort characters by frequency, and LeetCode 692, top k frequent words, also involve working with frequency counts and sorting. Exploring these problems can deepen your understanding of related techniques. As for alternative approaches, one option is the sorting approach, where you sort the array and then iterate through it to find the largest unique number. While this reduces space usage to O(1), with in-place sorting, it adds O(n*log n) time complexity. Another approach is the two-pass hash map technique. Here, you use the first pass to count frequencies and the second pass to identify the largest unique number. It's efficient, with O(n) time complexity and O(n) space usage, but requires two traversals of the array. Finally, there are some additional techniques to consider. The single-pass hash map approach is highly efficient, as it tracks frequencies and maintains the largest unique number within a single traversal. While this reduces time complexity to O(n), it requires slightly more complex logic to manage everything in one pass. Another option is the set-based approach, where you use one set to track duplicate numbers and another to track unique numbers. At the end, the largest remaining unique number in the unique set becomes your result. This method is intuitive and straightforward, but it requires additional space for the two sets. Depending on the constraints of the problem, these alternative approaches can help you choose the most appropriate solution for your specific use case. Great job! We've solved the problem of finding the largest unique number in an array. We reviewed the algorithm, analyzed its complexity, and discussed key takeaways. Remember to practice similar problems and apply these concepts in your coding journey. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!